LinkedIn pushes 80 million messages every second through Kafka. Not a typo. Every second. Traditional message queues would collapse under 1% of that load. Kafka doesn't use a smarter algorithm. It uses a different mental model entirely. Think of it like a post office that ditched filing cabinets for conveyor belts. That swap changes everything. Old school queues like RabbitMQ store messages like a filing cabinet. Sorted, searchable, deletable. That works fine at 10,000 messages a second. At 1 million, the cabinet jams. Memory fills up, disks thrash, and the system chokes trying to find and delete every message it just handed out. Here's the physics problem. Random disk writes can be 1000x slower than sequential ones. A filing cabinet needs random access. Find slot 4382, insert, close. Every insert is a disk seek. At scale, those seeks bottleneck you long before the CPU even breaks a sweat. It gets worse. Traditional queues delete messages the moment they're acknowledged, meaning per message, per consumer tracking. Multiply that by 1 million messages a second, and you get memory exhaustion, nonstop garbage collection, and compaction jobs eating CPU just to stay afloat. Here's what nobody tells you. Kafka never deletes a message when you read it. Messages sit in the log until a retention timer expires, hours or weeks later. Reading doesn't touch the log at all. That single decision removes the entire deletion bottleneck that kills traditional queues. Remember the conveyor belt? That's literally Kafka's storage engine. Every message gets appended to the end of a file, never inserted, never edited. No searching for a slot, no random access. Just write in order. This is the commit log, and everything else builds on it. The numbers explain why this works. A spinning HDD writing sequentially sustains 100 to 200 megabytes per second. That same disk doing random writes crawls at 0.1 to 0.5 megabytes per second. Sequential writes can be 1,000 times faster on identical hardware. One conveyor belt still has a limit. So Kafka splits each topic into partitions. Independent, ordered logs running in parallel. A topic with 100 partitions is really 100 belts, side by side. Producers spread writes across them, consumers spread reads. Parallelism built into storage itself. Partition count is your main scaling knob. More partitions means more parallel writers and readers. But it's not free. Each partition is a file handle, and replication multiplies network traffic. Senior engineers size partitions to their throughput target, not gut feeling. Now the network problem. Traditionally, sending a message means 4 copies: disk to kernel buffer, kernel to app, app to socket buffer, socket to NISC. Each copy burns CPU. Kafka skips straight to the network card with a Linux trick called zero copy, cutting 4 copies down to 1. Here's the trick engineers use: the sendfile system call. The broker tells the kernel send these bytes straight from disk to that socket, and the kernel does it directly without Kafka's process ever touching the data. Kafka never inspects the message. It just moves bytes. This is exactly the config a senior engineer would ship. Ax equals all for durability, compression turned on, and linger.ms lets the producer wait 5 milliseconds to build a fatter batch. Every setting trades a sliver of latency for a massive gain in throughput. At 1 million messages a second, the producer batches 5,000 messages every 5 milliseconds. Compressing similar JSON together, not one at a time, hits a 10x compression ratio. 500 kilobytes becomes 50. One network trip replaces 5,000 individual sends. On the read side, consumer groups split the work. Each partition belongs to exactly one consumer. Never shared, never duplicated. A 12-partition topic with 4 consumers gives each one 3 belts. Add consumers, and the work automatically rebalances. But there's a ceiling. Consumers beyond your partition count sit idle. 12 partitions means 12 is your max useful consumer count. This is exactly what interviewers ask. What happens with more consumers than partitions? Now you have the number attached. Instead of tracking acknowledgements per message, Kafka tracks one number per partition, the offset. Consumer reads message 5000, processes it, commits offset 501. Crash and restart? It resumes exactly there. No lost messages, no per message bookkeeping. One counter doing all the work. Durability comes from replication, not paranoid disk syncing. Each partition has a leader and typically 2 followers. Reads and writes hit the leader. Followers continuously pull and replicate. If the leader dies, a caught-up follower in the ISR takes over instantly, 0 data loss. You control durability versus speed with one setting, Ax. Ax equals 0 fires and forgets. Ax equals 1 waits on the leader only. Ax all waits for every in-sync replica. In an interview, say, ax equal is what you use when losing a message costs more than milliseconds. Put it together. Producer batches and compresses, sends one network call, broker appends sequentially, replicates, acts back. Consumer fetches via zero copy, commits its offset. 9 steps, each engineered to avoid a bottleneck. Not one trick, 9 small ones stacked together. Zero copy alone gives 2 to 4x throughput. Batching and compression add another 10x. Sequential I/O saturates disk bandwidth instead of fighting it. None of this is an exotic algorithm. It's refusing to fight how disks, kernels, and networks actually work. This isn't theoretical. LinkedIn, Kafka's birthplace, runs thousands of brokers processing over 7 trillion messages a day, peaking near 80 million a second. Every page view, click, and database change flows through this exact architecture before hitting a data warehouse. Uber streams a location ping from every driver every 4 seconds, millions of drivers globally. Kafka feeds those pings into Flink, computing driver density per map hexagon in real time, driving surge pricing in under a second. Over 1 trillion messages a day just for dispatch. Netflix treats Kafka as its central nervous system. Every click, every viewing session, every recommendation signal passes through Kafka before hitting downstream systems. It's not just a message queue anymore. It's the connective tissue between hundreds of microservices. This breaks everything you think you know. More partitions isn't always the answer. Too many means thousands of file handles per broker, slower leader elections, heavier replication traffic. The senior move isn't maximizing partitions, it's sizing them to your real throughput target. In your next system design interview, say exactly this. Kafka gets its speed from sequential disk writes, zero copy transfer, and batching, not from being in memory. That one sentence signals you understand the architecture, not just the API. Zoom out and the whole story is one choice. Naive queues built a filing cabinet and paid for it in seeks, memory pressure, deletion overhead. Kafka built a conveyor belt, append, batch, replicate, stream, and let the operating system do the heavy lifting. Kafka's speed was never a clever algorithm. It's a conveyor belt architecture that works with disks and kernels, not against them. Next time someone asks how Kafka hits 1 million messages a second, tell them, it's not magic, it's alignment. Subscribe for the next breakdown.